Down. Oh, I have no way of knowing. Fuck it. Whatever. Does not matter what I was even trying to say because I didn't get it out. Alrighty. Time to continue. Alright. Mate connector. Oh,
Let's take a look at Onshape's powerful drawing capabilities. We'll start by viewing a few completed drawings, then move on to creating our own. First, navigate to the Drawings folder using the tabs along the bottom. The main assembly drawing showcases our vise assembly in an exploded state, with the full bill of materials and detailed callouts. While the sliding jaw drawing contains detail views, whole callouts, GD&T, metadata references, and more. These completed drawings highlight just some of the numerous professional tools available in Onshape drawings. But now, let's create our own. Navigate to the Jaw Parts Part Studio. Then, right-click on the Jaw Pad Static part in the parts list and select Create Drawing. Choose any of the available templates and select the 4-view option. Note that you can also create your own custom drawing templates. Change the isometric view to a shaded view by right-clicking, selecting Show/Hide, then selecting Show Shaded View. Let's add some dimensions. Select the Dimension tool and define the height and width of the front view. Note that you can add tolerancing and other dimension details by hovering over the dimension. Feel free to add the rest of the dimensions to fully define the drawing. Next, let's update the sheet metal plate drawing to reflect the changes that we made in the Part Studio section. Navigate to this drawing and click the yellow Update button to update the drawing. Now that holes have been added to the drawing, let's add a hole table. Select Hole Table from the toolbar and click the Flat Pattern view. Then, define the origin as the bottom left corner of the flat pattern. Finally, relocate the table to the bottom left corner of the drawing sheet. And we're done. Nice work.
Nice. Might mute my mic.
Okay, so I want to explain why it was always why I left so like that. What's it called? There I pulled up boom flower.
All of the data we've worked with so far was natively built in Onshape. But Onshape also has functionality in place to import CAD data in just about any format. Let's import some geometry and show how it can be manipulated and integrated with our Onshape assembly. Download the new locking screw step file by clicking the link above this video. Then, from the plus menu, select Import. Find the locking screw.step file you just downloaded and confirm the import. Select the Combine to a Single Part Studio option and hit Import. Details of the various import options can be found in the Learning Center. A new tab will automatically be created with the parts contained in the locking screw assembly. The screw we just imported is too long, so let's model cutting this vendor part. Onshape has a suite of direct editing tools that can be used to manipulate imported geometry, such as Modify Fillet, Delete Face, Move Face, and Replace Face. Use the Move Face feature to move the top face down 3/4 of an inch. Next, use the Modify Fillet tool to remove the fillet. Even though there is no fillet feature associated with the imported geometry, Onshape recognizes this face as a fillet and is able to delete this filleted face. Let's go ahead and insert this screw into our assembly. Navigate back to the Base Subassembly tab. Select the old handle and screw, right-click, and delete these parts. Then open the Insert menu. Select the entire Screw Part Studio, click anywhere in the graphics area, then confirm the insert. Let's mate these parts together to constrain their motion. Create a revolute mate between the middle of the pin and the middle of the handle. Then, add another revolute mate between the end of the pin and the edge of the hole in the screw. Next, add one final revolute mate between the screw and the locking collar. Finally, let's restructure the locking screw parts into a new subassembly. Select all 3 parts from the instance list, right-click, and select Move to New Subassembly. Flying out the bill of materials and switching to the structured view allows us to see the effect of this change. And, right from Onshape's bidirectional bill of materials, we are able to update the name of this new subassembly. Great work! Feel free to play around with importing your own data into Onshape and explore the many ways Onshape allows you to work with imported geometry.
So what I have to do now is bring in the geometry from FreeCAD into Onshape because it's currently just file data at the moment. But yeah, about to go silent again. Because it doesn't really require me to talk much. Whoop-dee-whoop-dee-doo. Yay. Oh, the shit that failed. Alright. Let's disappear again. Bye bye. Alright, I'm back. Alright, let me import the rest of the parts in so I can leave FreeCAD. This one, insert. Three. Alright, now let's import. There we go. That sounding fully work. So I can actually do this properly. Also, where's the car studio? Okay, how do I? I do not get how I can find the photo inside of that. I get it. Alright, it's time for me to go to the learning center. Because I don't know what the hell I'm doing. one thing before I go in there. How do you draw? Sketch. All the tools are there. How the hell do I start a line? Is a spline? There's a line. Wow. Look at that. I gotta figure out how to stop my thing from sketching. I have no idea. Anyway. Enough of that. I should be able to extrude. Wow. Look at that. Very first sketch chart. Already an hour long. Love to see that.
CAD, or computer-aided design, is a tool used by engineers and designers to bring their ideas to life. CAD is used to model and engineer designs, allowing engineers to visualize, test fit, and explore how mechanisms function before prototyping or manufacturing. CAD provides users with an efficient and robust engineering environment to test, design, and implement their ideas. It is used in a vast variety of fields and industries, including automotive, aerospace, architectural design, product design, machine design, and several others. Designing in a CAD system enables engineers and designers to iterate on designs quickly and inexpensively. CAD models can be reviewed, analyzed, and updated, ensuring the design is operational and safe before beginning the prototyping and manufacturing stages. CAD saves resources and costs by reducing errors, miscalculations, and time to market. To better appreciate the advancement of CAD, it's important to look back at how the design process has evolved. The history of CAD is a fascinating story, spanning a nearly 60-year-long timeline and incorporating multiple technological and platform shifts. For a full and excellent narrative, please feel free to browse cadhistory.net. The nutshell version is a story that steps from a completely manual process using drafting boards through some of the earliest software work in relational geometry from people like Ross, Cohen, Sutherland, all the way through to today's distributed software as a service platforms. The early work on hardware and software was largely academic until the mid-60s, when for the first time, the availability of commercial mainframes in the deep pockets of the largest corporations, such as GM, General Dynamics, and others, enabled the application of these technologies to commercial and military purposes. These systems were expensive and primitive by today's standards, largely duplicating the wireframe manual drafting process, and ran on proprietary hardware, but it was a start. By the 1980s, we had the next platform shift: the personal computer and the x86 instruction set chips from Intel. With Office computers and the arrival of a certain company, Marin Software Partners, that later became Autodesk, affordable computer-based drafting in 2D became available. In parallel to this migration to the personal computer, another startup successfully married the emerging technology of solid geometry kernels to the Unix desktop workstation. Much of the research was done at Cambridge University, UK, and commercialized by a number of prior companies, including Matra Data Vision, Euclid, and others. The Unix desktop workstation could handle a significantly greater computational workload. The startup in question incorporated in May 1985 as Parametric Technology Corporation, or PTC. And while not the first solid modeler, it did introduce the concept of parametric features, or the formulaic sequential regeneration of a model. The next platform shift was capitalized on by the 1993 incorporation of Winchester Design Systems that later became SolidWorks, and the 1994 commercial release of a product by the same name. This time, the new platform was a standardized interface of the MS Windows operating system and UI development tools that worked across x86 hardware platforms. SolidWorks was also the first large-scale commercial CAD application that made heavy use of off-the-shelf technologies for core capabilities: Parasolid for the kernel functions and D-Cubed for 2D and 3D constraint solvers. 3D parametric feature-based CAD has become the standard for manufacturing and design companies. As companies rely more and more on these systems to innovate and design, more and more data is generated. To keep all the files protected and revision managed, companies invest in product data management, or PDM, and product lifecycle management, or PLM systems. These systems protect data in a vault, require a check-in, check-out process, and revision manage the designs. They allow companies to track a design from conception through the engineering process, and in the case of lifecycle management, to the end of its life. In large companies, intricate IT networks are installed by CAD administrators to achieve the level of data integrity needed.
That?
Manufacturing has become globalized, and the supply chain has significantly expanded. Intellectual property from the CAD system is needed by vendors, suppliers, or shops to manufacture designs. No longer is every aspect of a design manufactured or created in-house. Files have to be emailed and copies of data are made, creating a data disaster. Engineers have trouble understanding which file is the latest revision of the design, which one was sent to the supplier, and left wondering about the security of their data. Many companies operate in this stage today. Following a long stagnation and platform evolution, the explosion of cloud, web, and mobile that grew exponentially since 2005, software as a service and the social web have become the new standard for business-to-business and business-to-consumer interactions. Think about this. When SolidWorks was launched, none of these companies existed. Google, PayPal, Facebook, Amazon Web Services, Salesforce, Snapchat, Uber, or Twitter. The power and accessibility of this new platform, harnessing the cloud, along with its inherent collaborative capabilities, was a huge draw for luminaries like Hirschtick, McElhenney, Harris, Lee, Lauer, and Corcoran to build a new CAD offering. Incorporating as Belmont Technologies, later Onshape in 2013 and entering full commercial release in 2015, Onshape capitalized on scalable cloud computing, the advanced data security offered by AWS, and a zero IT footprint to offer a compelling alternative to aging desktop software. With frequent releases and a completely fileless database architecture, today Onshape stands alone as a full cloud professional-grade 3D design and data management platform. The invention of CAD revolutionized the way engineers work and continues to evolve with the power of cloud-based computing, as demonstrated by companies pushing the forefront of technology like Onshape. Parametric CAD is a workflow that captures the steps, or sketches and features, used to create a model. Relationships between features are established, allowing a user to edit previous features, and updates to related features propagate down the list. As new features and sketches are created, they are added to the bottom of the list, or where the rollback bar is positioned. This allows the users to make any changes to their model without compromising the other characteristics and features that exist. The feature list captures the sketches and features that were used to create the model, defining the recipe of how the part was built. In this example, the part contains sketches and features defined by their parameters. There are features towards the bottom of the list that depend on features above it. By making some quick dimension edits to features higher in the list, dependent features further down the list are updated to reflect the changes. For example, editing the length of a dimension in a sketch updates the length of the feature the sketch is associated to. This part is contained and instanced in an assembly. Editing the parameters in the sketches and features updates the part, and in turn all the instances of the part contained in the assembly reflect the changes as well. A variety of fields use parametric CAD to create designs and models. It gives engineers and designers the ability to create models defined with the needed design intent. This allows them to update the model quickly when changes occur. It is a modern approach to product design and a manifestation of the engineering design process. Spatial reasoning is a skill that refers to the capacity of thinking about objects in 3 dimensions and drawing conclusions about those objects from limited information. This skill comes in handy when packing a car for a long trip, playing Tetris, completing a Rubik's Cube, or solving engineering challenges. When creating models in 3D CAD, spatial reasoning is a skill an experienced CAD user has mastered. This helps the user understand how to model the needed part geometry and assemble the parts together. In most 3D feature-based CAD systems, parts are created by visualizing and sketching 2D profiles, and then using those sketches to create 3D features. Parts are composed of several features built on top of each other, defining different aspects of the geometry. To be an effective CAD user, the designer must understand and visualize how to build the part from a series of sketches and features, which are the basic building blocks used to create geometry. Spatial reasoning is a key skill to this process, because it allows the user to visually manipulate objects in various ways. This is important when modeling, because a CAD user must understand their model mentally first. Then they are able to construct
Amazing
the parts by
music for
utilizing the features a CAD software offers. Finally, the user assembles the parts and defines motion between them in an assembly. Visualizing how a design comes together by performing spatial reasoning tasks is vital to becoming a master CAD user.
Which 3D object results in folding the development around the gray face? Alright, so if you fold the development, I'm assuming they're referring to this face, right? You fold this up, it's gonna be flat. Fold this up, it's gonna be flat. When these two meet, it's gonna be a pitch right here. When you fold this up, it's gonna create a straight line here. This is gonna angle down. Fold this up, you're gonna have a square here with half of this shooting down right here. Then you have these two. When this reaches here, now this is gonna fold down this side over here. No, this is on the top. What am I saying? Creating. And this ends up here. It's gonna go like a slash like that. And then this will be right here to further go down. So it's pretty much this. It's B. Unless I'm tripping. I'm pretty sure it's B. Yeah. Ha ha ha! Ha ha! Alright. This is rotated too. Okay, so it's rotated this way. As this is rotated too. It's rotated this way, the same direction. This one, this direction. Taking it right there. We rotate this in this direction. Rotate this matter like that. This matter block here. Bulk. Yeah. It's looking like it's B again, guys. It's looking like a B. Which 3D object results in folding and development around the face? So we fold this up. It's standing up. Little line, little down, little dent in. And then this is gonna fold over halfways across that, then fold down, and either fold out. What does it turn into, a revolve? Oh, yeah, so you fold this up, Then this revolves around here, creating a little section right here that's lower. This folds here, then that folds down here, leaving this. Does that fold back in? Or does it fold out? If it folds out, it creates something here. If it folds in, then it would complete this lower circle. Wait, no, by the time this folds down, well, no, it'd be right here. The folding point is here. Actually, it would be like this. Aha! Huzzah! Alright. Special reason. What the hell? This is rotating to this. Oh, that's this right here. So this edge ends up here. So this is just spun this way. So this needs to be spun this way. So where they're both flaring out from the ground. Right? Because this corner here ends up here. Which means this corner should end up here. Obviously, you can't see that side. It's weird. Unless you just make it roll in the plane, but that doesn't roll. Like this rotates exactly. This should be the bottom. Is rotated to this. As this. Rotate it this way. Brings this end, puts it here. Brings these two ends, and puts it in my face. I'm really losing it on this one. What the heck? Lucy, can I zoom out? So you can see it all in one picture. This is rotating. Well, actually, this would have to rotate that way to be that. This would have to rotate this way to be that. This would have to rotate. I'm gonna just go with C, but I feel like it should look different. Yeah, I feel like it should look different, but that's fine. Alright, let's zoom back in. One of my little brothers can get this. I fold this up. Fold this up. Now you have angle going across here. It's only viewable from the back. Because when this goes here, this is going to be all the way up here. And on the back end is going to be this. That's interesting, regardless. Anyway, this is going to fold up, creating a plane that slants down here. And then when this folds over, so when this ends up here, it's going to fold down to fill in that mini little square. This area will be filled in by that square. No, it can't, because there should be a square right here where it is. Hold on. Let me see this. I got this one not because I'm wrong, because I didn't read the letter properly. I'm really looking at C thinking it's B. Oh my goodness. Absolutely gone. Like, come on. Would have had a perfect score. No, I don't. I literally make the exact same mistake seconds after. Why do I keep thinking it's corresponding to the letter below it and not the one above it? Come on. I'm still incorrect? No way. It goes up, right? Oh, wait. That's because it's on the first one. And then the second one this would be here on the first turn, right? And then now I have to take this triangle and half of this to go into the ground, which would look like this. A. Am I losing it? I thought I was so good at this. It goes up and it goes over. Unless they have it going the other way. But in the same vein of reference, it's still gonna have the same orientation. This feature is here, whether you go 1, 2 or 1, 2. So this feature that's at the top should be pointing down. This should be in the ground as well. Flip this up, bring this end, so this end here and this end here. If you spin it, it could look like this one. But then I already pixie. What am I doing? It's because of this. This is messing with me. And also the fact that this is offset already. So this would be here. And then it goes here. This would be here. Alright, when it's flat, and then it would be here. So I should be seeing the back side like this, forming a triangle, because this end, which was here after being spun, would be here. Same way how on this one it's this end that I'm seeing here, not this end. So I need something in the front plane. This would be here. Then it would be here. So something like this. Cannot be this. Let me zoom out so I can see everything in one. That's what would be forming that angle. Either D or E. Yeah. Goodness. That one was a doozy. It's starting to get to my head now. These ones are actually difficult. Never had to do some madness like this. My mic is still picking up my voice, right? It is. Alright, so we angle this up. Now we have a backbone for this. This angles up, connecting with this, and giving us a slope here with two triangles for two squares on a slope. This angles up, this gives us a triangle right here, meaning that this is going to be a slope right here, going down like so. The triangle here to add into this. What the hell is over here? This is difficult. Probably something like this. Only problem is forming triangles. So it cannot be this. However, it can be these two. But there's no square at the bottom. Only squares at the back. So it cannot be this one. It has to be. Yeah. Spatial reasoning. Rotated so that this end is here. Bro, what is this torture, dog? Like, yo. Oh my goodness. No, it's actually not even rotated like that. It's rotated like this. This end ends up here. So this end is rotated once, and then again, 90 degrees. So this needs to go here, and then here. It would sit up to where this face is facing me, and then it'd spin again, most likely to look like A. You wouldn't be able to see anything because it would be backing you. Yeah. Whew, this is difficult. This is some advanced challenge talk. Damn. Alright, this square here to form this square here. To form a slope. It doesn't even have to be a slope. It could be like this. Oh, they meet here. So currently we have this right here, right here, this here. With no top plane, of course, because why would we need one of those? Then here comes this. This origami guy? Like, jeez. And this folds up. This folds over here. This would be over here, creating a high tower. A tower that is higher than this one. Can't do this. This angle does not exist to be created. Can't do this either. Unless you guys are rotating. If you're rotating it, y'all are foul. There's no reason you should be rotating. But I have a feeling it's one of you rotating it. Because none of these are going to shape here. Move it this way. These are all the same height, this is all different height, so there should be a slight between this and this. Shit's giving me a damn headache. This part right here is high. If this comes here, and this is this height, this part's lower. Right? So you look for one that has a slant that goes from the inside of the shape to the outside of the shape. As far as openings or spaces, big spaces, when this folds up, this folds over, creating a line here. The next one folds down, and then creates this, which we see here. This is giving me a headache. Dog. This shit is hard. Alright. Okay, so this looks like it's rotated 2 different directions. Because that hole's here. You rotate it up and then spun around. So, rotate it this way to bring this here. Now, rotate it up so that this is facing me and then spun around. So that would be the equivalent of rotating it. So this is here and then spinning it around. Kind of like this. Because it's rotating so that this is here. And then spinning it. So that you're only seeing these two. This is here. If you rotate this up, this would be here. Then when you spin it around to bring this here, you might see, it might be see. My brain's getting fried, like seriously. Oh my goodness. Nice. Jeez, I need a break after that. I got a headache. Brain's fried. Alright, well, it was fun. Learning on shape, right? Alright.